Hello everyone and welcome back to our Elastic community channel. My name is Iulia, I'm a developer advocate for Elastic, and this is Elasticsearch 101. In today's episode, we're going to dive into how Elastic works behind the hood. We'll be exploring concepts such as cluster, node, shard, index, scalability, and much more to figure out how does data get into Elastic, how is it stored, and most importantly, how is it retrieved. So let's dive into that. In previous episodes, we've discussed how Elastic is basically a document data store, how we have these JSON objects containing key and value pairs that are stored in an index and can be retrieved based on those values that we want to query. It's quite similar to a classic relational database, but it works with different types of requests that we make to the server to get back our nodes, to put new documents in, and to search through them. But what does this server look like? Firstly, it's important to note that Elastic is based on Lucene, which is an open source search framework that we also occasionally contribute to. Understanding how Lucene works is at the core of figuring out how Elasticsearch works and how it builds upon this to provide additional capabilities. The main concept we need to explore when it comes to Lucene is the way that it stores documents. Everything about how Lucene stores documents is meant to make these documents easy to find and retrieve. After all, we're creating a search engine. Let's say we want to search for information and this information is stored in a book. Rather than entering a room where a big pile of books lays on the floor and you have to go one by one and try to figure out what the information you want is, you go to a library. The library has different rooms depending on the type of information stored, and in each room we have different sections. The sections can be split by author, by category, date of publishing, and so on and so forth. So if I know exactly what information I'm looking for, I can directly go in a certain room, in a certain shelf, at a certain row, and I'll know that the book I want is right there. This is basically what Lucene is trying to recreate as well, and we call that a reverse index. So rather than every time you get a new book, you throw it into a pile and say good luck to whoever wants to search through it, you have this meticulously arranged library. So every new book has an exact space that it belongs to, that makes sense, is reasonable, is next to other books of the same type, so whenever someone new comes in searching for something, it'll be very easy to direct them to where that information is. A lot easier to search. Now imagine that every instance of Lucene is an instance of this type of library. Within it, you're able to create your own index or your own categories of books, your own category of knowledge with whichever features you want to have in there. Publishing years, date, author, and all of these can be spread across the library in a way that makes sense so that you can search through it quite easily. Not only that, you have a lot of librarians working for you. Let's explore that. If an instance of Lucene is a library, and we only start with one librarian looking through the books for you, this will be called a node. When you create an Elasticsearch instance, you start with a node. This node is the system that allows you to search, so the library. However, the place where you actually store the data, say the shelves or the books, would be your documents, and these are stored in a shard. The shard is an instance of Lucene. This is where your data is really stored, and the node is what allows your data to be accessed, put in, or taken out. So this makes everything a lot simpler, right? If you're looking for a book, you go in and you go shelf by shelf in the category where you expect the book to be, and you get it out. But what if you have 50 people visiting the library at the same time? If we have one node and one single librarian, we would have to go and look through the entire library 50 times for all the 50 queries that have been requested. This might take a bit of time, and the queue of people waiting to get in and get their books might get a little frustrating. Now we can either scale vertically and say our librarian gets rollerblades and can go through the shelves a lot quicker, but there's a limit of how much better that can be. So there's a limit of how much CPU or memory or infrastructure strength this node has. So what we want to do is scale horizontally, hire more librarians. If we get a queue of 50 people coming in and we have 2, 3, or 5 people going through the shelves to get the books that they asked for, the process gets a lot faster. So basically we'll have multiple nodes that have the information spread amongst them, and they can each look for the books that we want. This way we can also hold more knowledge, more shards, more books, more shelves to look through, rather than a library that maybe could only have the capacity of 10,000 books. We can now hold 500,000 books because each section of the library can be managed by a different librarian. they also all communicate with each other. Rather than being independent nodes that don't have any relation and work completely in parallel, we're able to connect them through a transport or communication layer so that they can tell each other, hey, you're in that corner of the library, the book we need is there, I'm not going to walk all the way to you, you can bring it, and together we can complete this query. So the shards are spread across the nodes, and the nodes communicate and work together. That's because they're all part of the same cluster, maybe librarian union. And that's the very basic setup of how a very optimized library can get your books out as quickly as possible. Of course, it can get a little bit more complicated than that. For example, if a librarian has to call in sick and they're the only ones who know how to explore the historical section of the library, we might have a bit of an issue when someone comes in looking for information in there. So what we can do is we can set up replicas, copies of maybe the same type of librarian, so the same type of shard, that allows us to store the same information in a secondary location. If one librarian calls out sick, the second one can just come online or come into the library and cover the same information from a node that is still online. So the primary and replica shard live on two nodes so that they can't all be taken down at the same time. And if the primary shard goes offline, the replica shard comes in and does the same search over that part of your data. This is the concept of fault tolerance. If nodes go down, as they tend to in the technology world, just the same way that librarians have to call in sick, all of a sudden there is a system in place to pick the slack up and still work within the same cluster. So to recap, when you open Elasticsearch, you have a node. This is the system that allows you to search through data. On this node, you have a shard. This is the thing that holds your data, the instance of Lucene that has an inverted index, allowing you to organize your data in a way that will make it a lot easier to search through in the future. These shards will have replicas on different nodes so that they can be taken down at the same time, a principal and a replica shard. If the principal shard goes down, the replica will become the main shard of that data type, so that at any point in time, all your types of data are searchable and easy to retrieve. These nodes communicate with each other. They have a transport layer that allows them to split, divide and conquer, and look through different data in parallel and bring the results together. These nodes are part of the same cluster. So we have a very optimized library where a bunch of librarians cover different sections and different rooms, looking through all the books or shards, getting the information together from one node to the other, and working within this big cluster of books. And this is on the infrastructure side. At the same time, we have this higher level of organization called an index, which we've discussed in our previous document. This is telling us the kind of documents that we store, and we can have multiple types of index on the same shard, or we can have different solutions running at the same time over the same data storage facilities powered by the same nodes that search through this data. We can start simple, having only one index with a few shards on a single node, or as we scale out, we can have an index that maps to multiple different shards, multiple different nodes. The data is stored in many different buckets, but the index is able to access all of them and search the same information in a distributed way. Now we can also get a bit more specific. Beyond the concept of just nodes, we also have specialized nodes. Whenever possible, you can use these to optimize further the way that your library is being run or your search solution is being set up. You can have a master node that decides what the other nodes do and what they're assigned to. You can have data nodes that are specifically focused on storing data in various ways. You can have an ingest node that specializes on data being added to your library. And you can have machine learning nodes that are going to run your inference or your different types of models that you have that you can also add to your search process. So within a cluster, each node can have a special job, and they can still all work together to ensure that the library runs as smoothly as possible. Now, of course, this cluster can look quite differently depending on the type of solution you're building, but the important thing is that you have the power to customize it. If you want to ingest a lot more, if you want to store a lot more data, if you want to retrieve data faster, but you don't add data as often as possible, Elasticsearch allows you to customize how you're going to be working with your search engine so that you get the best results on the parts of the process that are important to you. So whether your solution is as bare bones as possible or an incredibly scaled out architecture with full tolerance, availability zones, and much more, or you're somewhere in between, Elasticsearch can help you set up the communication between the nodes, the distribution, the replicas, the communications within a cluster, the scaling, and so much more so that your solution runs as fastly and optimized as possible. And that's not all. In the next episode, we'll explore different types of queries and how setting these up can also affect the performance of your engine. Till next time, thanks for watching.